Hello, thank you for joining me. I want us to look at latent heat. Now, by latent heat is nothing but that quantity of heat that is extracted from a particular substance or that is added to that particular substance in order to change its state or to cause a change of state without a change in temperature. For example, I want us to look at what happens when a change of state occurs in a substance. We can use some ice cubes to experiment this. For example, we can have a heating curve or a cooling curve. But for this lesson, we are going to concentrate only on a heating curve. Now, if we have a heating curve, that means we can have a plot of either temperature versus time curve. So here we can have temperature is theta plotted in degrees Celsius against time. This time could be in minutes. So if we have something like this, let's say here we can have 0, 50, 100, 150, and we'll have 200 as the case may be. Maybe here we can have 1, 2, 3, 4, 5, 6, 7, 8, and what have you. Now, if you have a plot like this, and of course, here we can have, let's say, minus 50 from here. If we have something like this, and of course, for something like ice, and ice, dry ice we can have a negative 10 degrees Celsius, 20 degrees Celsius, 50 degrees Celsius, assuming we have negative 50 degrees Celsius. Now, if we heat it, once we heat, automatically we are going to get this shape. Now, on getting to this point, it can now maintain a constant value. Now, on getting to this value, it can now increase again. If it increases maybe up to 100 degrees Celsius, up to this point. So if it increases up to this point, and this is the boiling point of water, it can now maintain a constant temperature. Now, if it maintains a constant temperature, actually for substances other than water, maybe at this point now, this is the boiling. Of course, once you add, if you continue to add heat to this substance, it will just change because it has reached its boiling point. This water has reached its boiling point. The next thing we now have is vapor. Everything will turn to vapor. Now, I want us to look at this point, and this point, even this point too. So here we can observe that from minus 50 up to 0, we have increase in temperature. Now, on getting to 0, it maintains a constant temperature. So at this point, is the temperature is constant. So the temperature remains constant there. Now, after a while, let's say from this, it can now start to increase again. Now, this point is called the melting point. So we can call here as the melting point. So here is the melting point. This point. Now, in this process here, it is undergoing what we call melting process at this point. So immediately, all the ice cube is completely melted to water at 0 degrees Celsius. Now, there will be rapid increase in temperature until it gets to 94, 95, 96. It starts dropping. But the moment it gets to 100 degrees Celsius, maintains a constant temperature again, because at this point it moves to its vapor point or its vapor state. Now, this is a change of state. The change of state occurs between here and here. At this point, this is where the change of state occurs properly. So at this point, we have ice. We have ice here at this point. Now, this point, this ice completely melts to water. Now, here we have water at this point. Now, so change of state occurs from ice, which is solid, to water, which is liquid, and immediately after the liquid point, it can now move to vapor. So this is vapor at that point. So we now have change of state occurring from ice, which is solid, to water, which is liquid, and from liquid now into vapor. So continuous addition of heat to ice, or let's say solid body, takes it to its liquid state. Continuous addition of heat also takes it to its vapor state. Now, you can still take it the other way around. When you subtract heat from a substance, it can now, maybe from vapor, it can now, continuous extraction of heat from vapor will take it to liquid. From its liquid state, if you continue to extract heat, it will now take it to its solid state. Now, the point I want to drive here is that at this point, this melting process here, the ice turns to water at constant temperature. This one here at constant temperature. Therefore, we can now go ahead to explain latent heat as the heat required, either heat supplied or heat extracted from a substance in order to convert it from one state to another. Now, we are going to look at latent heat of fusion. Latent heat of fusion. Latent heat of fusion. Now, we can see that yes, latent heat of fusion is nothing but the heat required to convert quantity of substance at its melting point to its liquid form at constant temperature. We now have latent heat of fusion. Now, by latent heat of fusion, we can refer to as the entire mass. And of course, it is worthy of note that at this point, at this latent heat of fusion, or at latent heat, for latent heat, the heat here, temperature remains constant, that is number one. Number two, the thermometer does not detect latent heat. So since it does not detect it, that is why it is constant here. It does not detect it. Number three, latent heat depends on the mass of the substance or the nature of the substance in question. For example, we can have ice. Latent heat of fusion of ice is different from that of wax, candle wax. Of course, candle wax melts at a certain temperature. Of course, the temperature is constant. So the latent heat depends on the nature of the substance in question. Now, when a unit mass, or when 1 kg of this mass is involved, when 1 kg of this mass is involved, we now talk about specific latent heat, heat of fusion. Now, when we say specific latent heat of fusion, we mean that quantity of heat required to change a particular substance at its melting point from its solid state to its liquid state at constant temperature. So that is what, the quantity of heat is required to change unit mass or to convert unit mass of a substance from its solid state to its liquid state. That is what at constant temperature. That's what we mean by specific latent heat. Now remember, at this point it is liquid. Now here now it is vapor. Now since it is vapor, we can still note what you have there. So at this point here, we now have what we call specific latent heat of vaporization here. Now the specific latent heat of vaporization is nothing but the quantity of heat required to convert unit mass of a substance at its boiling point into vapor without change in temperature. Now, we'll come back. Specific latent heat of fusion of a substance is represented by L. It's represented by L. Therefore, the quantity of heat required at this point is expressed as Q equals ML, where Q is the quantity of heat, M is the mass of substance, L is the specific latent heat of fusion, fusion of ice, the specific latent heat. Please permit me to use abbreviation. Specific latent heat of fusion of ice. Specific latent heat of fusion of ice. And of course, it is a constant value. Most times, you might be asked to get L given Q and M. Now we can take the SI unit. So the SI unit of specific latent heat is, of course, if we make L the subject, we now have Q over M. Now if I have Q over M, Q, which is the quantity of heat, which is measured in joules, M is measured in kg. Therefore, the SI unit or specific latent heat is joule per Kelvin. Sorry, joule per kg, please. Joule per kg. Now, in summary, we can now have here, remember we said heat supplied to ice takes it to water, and if you continue to add heat to that water, it takes it to vapor state. Therefore, at this point, there is change in temperature. Because there is change in temperature, Q is equal to MC delta theta at this point. At this point, which is MC delta theta. Now, at this point now, Q is ML because there is no change in temperature here. So here, well, this C is a specific heat capacity of the ice here, while delta theta here is the change in temperature of this. Now, we cannot have, at this point, where the temperature rises. Now, when the temperature rises, we cannot have Q is equal to MC delta theta at this point. So, at this point, there is a rise in temperature here. At this point also, there is no change in temperature. So, the temperature is constant. We have this. At this point, there is a change in temperature. Now, when it turns to vapor, Q will give us ML. L here is the specific latent heat of vaporization of steam at this point. Specific latent heat of vaporization of steam. Now, the entire heat all together. So we can have, if we have here as, we can have here as Q2, we can have here as Q3, and we can have here as Q4. Now, the total heat involved in this process, assuming you are asked to calculate the total heat taken to convert a certain mass of ice at minus 50 degrees Celsius to, let's say, a steam at 100 degrees Celsius, we can now calculate that Q will now give us Q1 plus Q2 plus Q3 plus Q4. So that is the total heat required in this process. So let us take one or two calculations to help us better understand this. Calculate the quantity of heat required to convert 200 grams of ice to water at 0 degrees Celsius. Given that the specific latent heat of fusion of ice is 336 joules per gram. Now, how do we solve this question? Solution. Now, the first question we ask ourselves is, they said the quantity of heat required to convert the mass given to us here is given to be 200 grams. Now, the specific latent heat of fusion of ice here is 336 grams, joule per gram. Because this one is in grams, leave this one in grams and then continue. So, with our question, remember that they said theta here is 0 degrees Celsius. Now, that means the conversion is done at a constant temperature. Because it is done at a constant temperature, we can now have that Q is equal to ml, which will give us N is 200 times L. L is 336. Therefore, we can now have that the quantity of heat required in this process is 200 times 336, which will give us 67,200 joules. Or you can still have it as 6.72 times 10 raised to the power. We can shift 1, 2, 3, 4. We can shift it like this. And it will now give us 6.72 times 10 raised to the power 4 joules. So that is the solution to that problem. Now we take the second question. Now the second question says, calculate the total amount of heat required to convert 0.5 kg of ice at minus 15 degrees Celsius into water at 90 degrees Celsius. Now here we have the specific heat capacity of water, 4,200 joules per kg per Kelvin. Specific heat capacity of ice, 2,100 joules per kg per Kelvin. Specific latent heat of fusion of ice is 36,000 joules per kg. Now we solve it straight. Now the best way to solve this particular problem, given the values that are given to us, are we have the specific heat capacity of ice given to be 2,100 joules per kg per Kelvin. Now, specific heat capacity of water here is given to be 4,200 joules per kg per Kelvin. We are given that here, specific latent heat of fusion of ice is given to be 3600 joules per kg. Now, with this in mind, remember they said the temperature change here is from minus 15 degrees Celsius to 90 degrees Celsius. In other words, it will take this process. Now, the first step is, because this is, the mass given to us is given to be 0.5 kg. Now, with all this in mind, the first thing we are going to do is heat that will convert this minus 15 degrees Celsius to 0. Now, I'll say heat required to convert ice at minus 15 degrees Celsius to ice at 0 degrees Celsius. From minus 15 somewhere here to 0 will give us Q1. We can call it Q1. And this Q1 will give us MC delta theta. Now the delta theta here now is from 15 to 0. Now which will give us the mass is 0.5 times specific heat capacity, because it is ice, specific heat capacity of ice, which is 2100 times temperature change, because it is moving from minus 15 to 0. Use 15. This is cooling. 16. Use 15. Positive 15. This negative sign is just an indication that it is below 0. So we don't use the negative sign. So in other words, the heat required in that process will give us 0.5 times 2100 times 15 will give us 15,750 joules. So that is the heat that will take it to this. Now, the second stage is heat required to convert ice. At this point now, it is still ice. Ice at 0 degrees Celsius to water at 0 degrees Celsius. At this point, it is ice here. From here, it is here that the melting process will begin. So what will now give us Q2 equals ml. At this point, we will now have mass 0.5 times specific latent heat of fusion of ice, which is 3600, 36,000. Now 36,000, if I'm not mistaken, let me be sure. This is, 33, please. 336. 336, please. So we now have 33600, please. So if we have that, it will now give us 0.5 times 336,000, which will now give us 168,000 joules. Now this is where it is now. We have melted it to water at 0. The next thing, remember the question said from minus 15 to 90. So what we're going to do now is, it is now water at 0 degrees Celsius. We heat it up to 90. So we now have that heat required or needed to convert water at 0 degrees Celsius to 90 degrees Celsius. Will now give us Q3. Q3 is MC delta theta. At this point, C here is the specific heat capacity of water now. So which will now give us mass 0.5 times specific heat capacity of water, 4,200 joules per kg per Kelvin, times, and of course, temperature change here is from 0 to 90, which is 90 minus 0, which is still 90. And it will give us 0.5 times 4,200. 4,200 times 90 will give us, let's say Q3 is equal to 189,000 joules. Okay, you can screenshot this or pause it. Let us finish it here. Having gotten this, you can now say, therefore, total heat required, therefore, total heat required. Now, total heat required will give us Q equals Q1 plus Q2 plus Q3, which will now give us that Q is equal to, we can now take them one after the other, which is 15750 plus 168000 plus 189000. Now, total heat required to complete the process is 372,750 joules. Or you can say that yes, Q is equal to 3.728 times 10 raised to power 1, 2, 3, 4, 5 times 10 raised to power 5 joules. So this is the total heat required to convert a mass of 0.5, an ice of mass 0.5 kg at minus 15 degrees Celsius to water at 90 degrees Celsius. Last but not the least, estimate the quantity of heat required to melt 150 grams of ice at minus 10 degrees Celsius to water at 15 degrees Celsius. Given that the specific heat capacity of water 4,200 joules per kg per Kelvin, specific heat capacity of ice 2,100 joules per kg per Kelvin. Then specific latent heat of fusion of ice 360,000 joules per kg. So we now have solution. What we have here is that the specific heat capacity of water, is 4,200 joules per kg per Kelvin. Specific heat capacity of ice, 2,100 joules per kg. Then we now have specific latent heat of fusion of ice, which will now give us 33600 joules per kg. Now, the mass given here, the mass is given to the mass which is 150 grams. And of course, these ones are in kg. Because it is in kg, because they are in kg, we now have to convert this. If we convert this one, so we now give us 0.1 kg. That is the mass. Now, remember that the temperature change is from minus 10 degrees Celsius to 15 degrees Celsius. Because it is 15 degrees Celsius, the same process we took in the former question in example 2, we will still take the same process here. So we now have the first one here is quantity of heat needed to convert ice at 0 degrees Celsius to ice. Sorry, from ice at minus 10 degrees Celsius to ice at 0 degrees Celsius. So which will give us as Q1. Q1 is MC delta theta, which will now give us the mass here, our converted mass. Do not use this one anymore. So we now have 0.15 times specific heat capacity, because it is still ice. Specific heat capacity of ice will now give us 2,100 times temperature change. The temperature change now, because it is moving from minus 10 degrees Celsius to 0. 10, that minus is just an indication that yes, it is below 0. Do not use it, I repeat. So we now have times 10, which will give us that Q1 is 0.15 times 2,100 times 10. The other thing, Q1 will give us 3,150 joules. Now Q2 will give us quantity of heat needed to convert, now this is still ice, to convert ice to water at 0, to convert ice at 0 degrees Celsius to water at 0 degrees Celsius. So we can have it as Q2, which will give us ml. ml will give us mass of the ice, now see ice, mass of ice times specific latent heat of fusion, which will give us 0.15 times 336000, which will now give us that Q2 is 336000, will give us 50400 joules. Now Q3, quantity of heat needed to convert, now this is water now, convert water at 0 degrees Celsius to water at 15 degrees Celsius. It will give us Q3 equals MC delta theta at this point, which will now give us mass of water now, which is still the same mass of ice, 0.15 times specific heat capacity of water at this point, 4,200 times temperature change. The temperature change here is 15. The temperature change here is 15. So which will give us that Q3 is 0.15 times 4,200 times 15, which will now give us 9450 joules. Now, having gotten the heat at each level, we're not going to sum up the heat. Therefore, we can say that the quantity of heat Q required in the process is Q equals Q1 plus Q2 plus Q3, which will now give us Q1 3,150 plus Q2 50,400 plus Q3 9,450. Therefore, the total heat required in the process will now give us 3150 plus 50400 plus 9450. Total heat will now give us 63,000 joules, or we can now have it as Q equal 6.3 times 10 raised to power. Now we can move our point, which is here. 1, 2, 3, 4. We'll move it here. We now have this as our final answer. Okay, this is where we'll end the lesson. Please do well to join me in my next lesson, where I'll be bringing us latent heat involving electrical heat. Please, if this lesson was helpful to you, give it a thumbs up. Tell me something in the comment section, and if you have not subscribed to this channel, please do well to hit the subscribe button, turn on your notification button, and then we'll see in the next lesson. Thank you.